if we've got one here, looks like somebody forgot to turn on the lights again. It's awful dark in here. I can't find the light switch. Wonder where it is. Has somebody got a light or something like that? Oh, there we go. Ah, perfect. Look at that. Whoa, look at that smoke. That's a turbulent flow, that smoke coming off the match. You know, a fluid dynamicist might describe turbulence as a chaotic flow. However, as pilots, we describe turbulence as bumpy. Whoa, look at that. That, if I was flying in that would definitely be very, very bumpy. Whoa, hey, there we go. Delayed reaction. You know, things obviously when I'm in the studio don't move at the speed of light. Seems like everything just kind of is in suspended animation. Somebody turn on the lights, like maybe not the candle. Ah, there we go. Right on, that is perfect. Okay, we're back to normal, everybody. This specific subject is turbulence. And just like we saw with that match and that smoke and that candle, turbulence is sometimes a flow that is chaotic for the pilot. Now that said, it's very, very interesting to know that sometimes turbulence is induced because of our aircraft's motion through the atmosphere. So, turbulence is a result of either the motion of the air or the motion of the aircraft going through that air. We will often experience turbulence in a chaotic flow. That said, there's many times where we can experience turbulence in a smooth flow. How is that? Well, it's sometimes best to think of turbulence as a series of swirling bubbles or eddies. The strength and size of the eddies, as well as the airplane's speed and weight, will translate into different intensities of turbulence that we feel as a pilot. So for a moment, I'm going to go over to the whiteboard, and we're going to go through maybe a visualization of what these turbulent eddies look like. What I can first do is I can imagine the wind speed. Now, when it comes to turbulence, the wind can either be horizontal, as I'm diagramming here, or the wind motion could also be vertical. What we can then think of is as this wind moves, we end up with swirling sections. So we'll imagine that swirling section as that being the center of it, and then what we will have is we will have some sort of a rotation around that specific swirling point. So this eddy of swirling air could have a diameter. And this diameter could be anywhere from maybe, say, as little as less than even half an inch, or maybe on the scale of as much as, say, nautical miles wide. So the diameter could be small or it could be very, very big. So imagine this rotation as happening while this is moving through the airflow. So what's going to happen is this eddy, if we were to plot it, we could say, all right, well, imagine the eddy starting here, that certain radius, and now rotating its way around the center. If I was to plot that, it would start to look something like this. It'd be moving down, it's moving with the air, so now it's going to move and reach its bottom here, and then move back up, and it's going to start to use an up and down motion just like a wave. Of course, the wider the diameter, what will happen then is the longer the wave will end up being. So that's one way to start to think of turbulence. Now, before I go back to the presentation, what I next want to do is take just a few moments to think about what turbulence does to us as we fly our aircraft. So let's start out by thinking about updrafts and downdrafts. What do they do to our aircraft? Well, we can simply draw an imaginary wing. So, as we know, if you've studied general knowledge section already, theory of flight, we have the relative airflow, and then we have the relative airflow meeting at a specific angle of attack. This helps partly determine the amount of lift that we're generating. But let's imagine a case where one of those swirling eddies is suddenly coming from this direction. What you can now see is you can very quickly see that our angle of attack has changed. It's suddenly gone smaller because now the relative airflow is pretty much meeting this wing straight on. So what does that mean? Less lift, and guess which way the aircraft is going to go? Downwards. Now, of course, we could have another scenario. We'll imagine this airplane wing here again. And once again, we will have the normal airflow approaching. And in this case, let's imagine that now we suddenly have a very powerful updraft. What does that do to our angle of attack? Well, here it was originally at this size, and now it suddenly becomes much larger. So guess what's going to happen now to this wing? It's going to go upwards. And that's why when we're flying in turbulence, we start to feel these sudden pushes up and then sudden pushes down. Now in extreme cases, updrafts are the tricky ones because if this updraft comes very powerfully from the below us, that could potentially exceed our stalling angle of attack. So that explains why our airplane starts to go up and down in turbulence. It's often the changes in the angle of attack. But let's imagine another case. Let's think about our airplane, and then what about the side-to-side motion? So, if we start to imagine our airplane, then what we will do is we will think about the aircraft as the airflow approaches it. So that's how the airplane likes it. The airflow coming straight on. However, imagine a wind gust suddenly causes this airflow to suddenly come off from the side at a very much increased speed. Well, of course, what's going to happen to my airplane is it's going to try to yaw into that wind. It's because of all the pressure on the fuselage and the back of the fuselage. So the airplane is suddenly going to yaw hard to the right into this new wind. One final way that we can think of the effects of turbulence on us is imagine a case like this. So we're going to draw the airplane this time approaching us. And let's imagine that one of these smaller circulations of wind moving upwards, like that, suddenly only captures one side of my wing. Of course, what's going to happen is the airplane is going to roll like that. So turbulence really makes things more difficult for us as a pilot. It's constantly moving that aircraft up and down, left and right, and causing all sorts of things like roll. Now, if you've encountered very strong turbulence, you know that it can get very uncomfortable. Now, overall, the strength and size of these eddies, as well as the airplane's speed and weight, will translate into the different intensities of turbulence that we feel. I mean, we can have different sizes of eddies, but we also have different sizes of aircraft. And then we have those airplanes moving at different speeds as well. So all of these can cause turbulence to feel very different. So here are some of the factors that create the various intensity of turbulence. Large eddies are typically less turbulent unless we fly through them at high speeds. So you remember those eddies that I showed you that are nautical miles long? Well, if the eddies are way bigger than our aircraft, typically, if they're much larger, we'll just kind of gently be nudged up and down as we go through them. If we're moving through them at high speed, though, then things can be incredibly bumpy. The greater the wind speed, the greater the potential for turbulence. That makes sense. Think of that candle. If I blow it out gently, well, the smoke will wisp upwards afterwards very gently. But if I blow it out fast, well, that flow is going to be torn and shorn like crazy very quickly. Now, this rule applies particularly to flight at low levels. As I mentioned, an airplane that flies faster will experience more jolts. So the speed of the airplane is also a big determinant. Airplanes with high wing loadings tend to manage turbulence much better. Airplane of lighter weight will experience more turbulence simply because it is lighter. It's going to be easier for those eddies to throw that airplane around up and down. When it comes to turbulence, it is now broadly being classified into the following categories. We have what is known as clear air turbulence. We have mountain wave turbulence. We have turbulence near thunderstorms. And we also have low-level turbulence. And notice, like everything else in aviation, we like to give various abbreviations for them. I love this one here, TNT, turbulence near thunderstorms. As we know, turbulence makes flying much more difficult. Knowing what causes it can make your flight much more pleasant, though. This is partly because, hopefully, you can plan ahead and avoid areas where it might be lurking. So you will thank yourself and your passengers will thank you. And oh yes, of course, yes, there's real practical reasons for this. The exam is going to ask you many questions related to turbulence as well. So let's start to look at the many different types of turbulence that there are. We're going to start out with one of the easiest to remember, and that is convective or thermal turbulence. In this case, when you think back to the section that we talked about stability and instability on, we've got parcels of rising air. So these warm bubbles of air start to move upwards. Of course, they can form clouds. And it's within these parcels of air that things get really, really bumpy. I mean, imagine this airplane here that's flying in this level of convection. It's going to experience a lot of turbulence. Now, typically, what will happen is this area of turbulence will move upwards throughout the day as it gets warmer and warmer. But the initial trick is this. If you see a layer of, say, scattered or few clouds, you can legally fly above that. So that being the case, you could fly above the tops of the clouds. Convective turbulence will always end at the tops of the clouds. Now that said, remember, as it continues to warm up throughout the day, these clouds are going to continue to get higher and higher and higher, normally. Now, the other thing to remember is as this air goes up, right here in these zones, of course, we've also got air that is going downwards. Now, we'll also take a look for a moment at speeds through turbulence. And here's why, because glider pilots, they actually love these thermals. For those of us who are in powered aircraft, we tend to plow through these thermals, so that's why it seems bumpy to us. But a glider pilot who's inside of this thermal actually experiences very little turbulence because they're moving so slow. Let's go to the whiteboard for just a moment and show how that works. So what we'll start out with is we'll start out by drawing ourselves a series of arrows for the turbulence upwards. So maybe one there, maybe one here. Maybe we'll have another one that's maybe somewhere over here. That one's a little bit too close, so I'm actually going to erase that one, and we'll just give ourselves a little bit more space between these thermals. All right, so we've got our thermals here. And we have to remember that once we reach the top of one of these thermals, of course, that air works its way back down and sinks back towards the ground. So we'll throw those in here as well. Now, if I'm a glider pilot, and let's say that I'm just out here flying, and of course, in my glider, I might only be going something like, say, 45 knots. I'm going very, very slow. So as I fly, this little downdraft, oh, I'll feel it. My variometer will tell me that I'm going down, and I'll be a glider pilot. I'll be like, I don't like that very much. But then suddenly, I catch this gentle updraft here. And I'm like, oh, yeah, that's exactly what I want. And then I'll start to circle. And because I'm inside of that thermal itself, the entire plane is mostly in that thermal, I actually really won't feel turbulence. And I'm not crossing through these zones of up and down. Now, meanwhile, we get somebody in their high-speed business jet or something of the like. And now they are going at, let's say, like 400 knots or something almost. Now, they hit this, and before they can really do very much, they start to sink. They feel a powerful jolt. Then they feel the updraft. Bam! Another big bang as they suddenly come back down through here, and then back up through here, and back down through here, and then back up through here, and then back down through here. And by the time our business traveler is on this side, they're kind of like feeling really, really airsick and, something like that. So the speed at which our aircraft is moving through these cycles can have a huge, huge effect upon what we feel as turbulence. Okay, so we'll head back to the presentation then. Now, when it comes to convective turbulence, these cells are typically hundreds of feet in diameter. In unstable conditions, generally speaking, the more unstable the conditions, the quicker these will rise, a few thousand feet per minute. Now we've got fair weather cumulus. That will tell us that there's going to be bumpy flying. But don't forget that we could also have TCU, ACC, and cumulonimbus. So if you look outside and you see these cumulus-type clouds, right away I'm starting to think, okay, it's going to be bumpy, particularly so below the levels of the clouds. If possible, fly above them. And one thing that can cause convection as well as, say, solar heating in the summertime is a case where we have colder air suddenly moving over warmer land. Again, that could create some convection on us. So now we've got a little bit of a GFA chart for ourselves to give us a little bit of a practical bit of advice. When I look at this here, right away in this forecast, I can see things like ACC, TCU. So right away, oh goodness gracious, thunder showers, yeah. Definitely, if I'm flying in these zones here, I'm going to expect that it's going to be turbulent. And yeah, I'm going to need to watch out for these thunderstorms. Now, another thing to watch out for when it comes to the exams and writing the exam is that some people instantly go to the turbulence GFA to see, when they ask a question about turbulence, if there is any. Sometimes it might be blank. However, on the clouds and weather, you then suddenly see ACC or TCU. Well, we need to remember that whenever we have CB, TCU, and ACC, that they imply significant turbulence and icing. right? So not only do we need to take a look at the turbulence chart to see if there's turbulence expected on that day, but we also need to take a look at the regular clouds chart to see what's going on as well. And then, yes, very practical for you too, as I said, to look at this and, okay, probably going to be a day where I'm going to encounter bumps. And yeah, you might not want to go depending on what time this forecast is for and how bad those thunderstorms are going to be. The next type of turbulence that you need to know about is mechanical turbulence. And in this case, mechanical turbulence is simply the fact that the air is flowing through various objects. That could be terrain, it could be man-made objects, and of course, as we have this flow moving towards something like this barn here, you can see this person has created a nice little runway right in there, and what initially was a fairly smooth flow as it strikes the barn suddenly becomes extremely turbulent. So now this poor little airplane here encounters significant amounts of turbulence. It makes it very difficult to land. The more unstable the air and the rougher the terrain, the worse this turbulence will be. That makes sense. The vertical extent of the mechanical turbulence in the lower levels would be greatest when cold air moves over a warm surface. Hey, wasn't that something that we said caused convective turbulence as well? Yes, it was. So cold air over warm air, that often creates problems for us. Now, here's another example of mechanical turbulence that I can think of where there was an accident that occurred and an aircraft was destroyed because of it. I'm going to go to the whiteboard and I'll quickly do a drawing to show you what happened in this case. What occurred in this particular case was a nice little windrow was made. So we'll imagine here that we've got our surface. And for the runway, we'll imagine that the runway was right in this zone like that. Now, sometimes what will happen is people will build their runways near rows of trees, thinking, well, that will be perfect because trees will help block the winds as they flow. And yes, they can. Sometimes what you'll encounter is nice smooth conditions as you take off. However, look out because, of course, aloft, we've got that very, very strong wind potentially flowing just above treetop level. This can create problems for us, though, because imagine now this flow as it comes off of the trees. A sudden downdraft, and as well, potentially turbulent eddies in through here as well. So imagine if you're the pilot coming in, and now all of a sudden you just get below tree level, you will have a sudden large sink, a loss of lift, and that air pushing you downwards. So that's one case. Terrain as well. We mentioned very briefly how terrain, so imagine we have two hills. So let's say we have a really gentle, smooth hill, something like that. But then let's say that we have a really steep hill, something like that. And in this case, we have the wind now flowing, profile view here, from this direction. In this case here, this little hill might be smooth enough and small enough that not a whole lot of turbulent flow encounters behind. However, now this steep hill, whoa, get overshot, and now I start to end up with eddies in behind here. It's kind of like a windshield. For those of you who drive Jeeps, if you've got the top down in the summertime and you can actually just take your head, and if this is the windshield right here, like this little hill, if you put your head in really close, you actually find that it's fairly calm right in behind the windshield. So, otherwise move out back a little bit, well, really bumpy, really bumpy. And that's what happens with a hill. Okay, so we'll head back to the presentation now. So it's a good idea when you are flying, if you've got winds, to carefully study the terrain and the objects that are around you. Think about that flow and how that wind will encounter those objects and what it's likely to do after hitting those objects. It's a little bit like when most of us were younger. You know, we would build great big like streams and dams and take the garden hose and then put the garden hose down, and then we'd watch the flow as it went through rocks and stuff and eventually filled up our dam, and then we would burst the dam and then everything would go all over the place. Ask yourself questions. What would the wind do? It's going to behave like water would. So here's some practical examples when it comes to the actual GFA. You can see the GFA will tell us the heights at which mechanical turbulence is expected. So right in here, we've got it showing moderate mechanical turbulence, and it's showing from the surface up to 3,000 feet AGL. In this case over here, it looks like I've got a low-level jet that's helping get that mechanical turbulence go. And yeah, there it is, mechanical turbulence, low-level wind shear. It says surface to 3,000 feet, again, moderate. In this zone here, all red, mechanical turbulence, moderate from the surface to 3,000 feet. Now, one thing to watch out for though, when it comes to mechanical turbulence, the only time the GFA will publish it is if it expects it to be moderate or severe. If it's less than that, it will not be in the forecast. Now, for those of you who've studied fronts, as you know, these are great big zones of two competing air masses. So, two competing air masses, we've got quite often very different temperatures. These can create turbulence as well. The worst ones, it's always cold air here, the worst ones are cold fronts. As you can see, we've got that cold air coming in, the warm air being forced very quickly. Maybe we would even have a low-level jet that forms along the front of this front. If that's the case, I'm going to end up with potentially quite a bit of frontal turbulence. Now, that said, we also could end up with frontal shear. Now, shear often causes turbulence, but not always, as we saw earlier. I just want to make the small distinction here between the turbulence and the shear. In this particular case right here, we've got shear happening. And that's because there's two very different wind speeds creating that shear, which has led to turbulence. We'll talk more about shear towards the middle of this presentation. Notice that fronts with temperature changes of 5 degrees or more may cause this happen. As well, it can happen at warm fronts and or cold fronts. Now, another mechanism that will create this, of course, is the speed at which the front is moving. So that would be the motion of the front in terms of this direction. So like that. The faster moving the front, the greater the potential for turbulence. Now, mountains really can do some very interesting things when it comes to turbulence. Think back again to that example that I said where, well, think about how water would flow over rocks. Air does the same thing when it's flowing over rocks, except for it's not visible until that air becomes saturated and it turns into clouds. When it turns into clouds, now you have all sorts of additional indicators that can help you see the actual flow. It is kind of nice because clouds will let you see the flow, but sometimes they might hide the mountains. So in this diagram here, we can see big mountain in the way, and we've got the overall wind flow moving from left to right. And, well, what's the air going to do? Of course, if it hits the mountain, it's going to start to flow upwards. Now, a single mountain all on its own, some of it might try to come around the mountain as well. That's possible. Once the air gets to the top, as I showed you on the whiteboard with those bigger, steeper hills, well, things get really interesting over here. Notice how this side is called the leeward side. This side is called the windward side. Now, typically, on the windward side, you're going to get some help. The overall flow is upwards. So that's good, an updraft for us. But yes, the various friction and stuff like that can create a little bit of turbulence on us. Depending on the conditions, the turbulence on the leeward side can get pretty nasty. So, knowing that, wind flowing from here, over here, here's where the turbulent eddies are. Notice as well that now we have that air flowing over, and then just like going over a waterfall, it goes down. So if I'm an airplane and I get caught in what we'll see in a few moments is known as a mountain wave, if I get caught in this severe downdraft and I'm flying towards the ridge, well, I'm just going to keep getting lower and lower and potentially crash into that ridge. So there's a little trick here. Always cross ridges at a 45-degree angle and give yourself at least 2,000 feet above that ridge. The reason for this is if I am this airplane flying towards the ridge and I notice that I'm caught in a downdraft, it's much easier to turn away from that ridge and head back towards the lowering terrain. So it's a safety valve. 45 degrees, 2,000 feet. Good rule of thumb for mountain flying and crossing ridges. So we talked about orographic turbulence, but let's now move into the MWT, mountain wave turbulence. At the lower levels, mountain wave turbulence can be some of the most violent turbulence in all of nature. As we've seen, typically the air flowing across a mountain range, as it goes upwards, it's fairly smooth. Once over the top, it pours down on the other side like a waterfall with significant force. It can bounce up and down after it has that first downdraft, and then that's where things get really chaotic. Powerful waves can extend hundreds of miles downwind from the range. These are typically the waves aloft. This here, waterfall turbulence, the rotor turbulence, and all those other good things at low level are a little bit, well, scientists are starting to differentiate between the two. The wave is higher and it goes for hundreds of miles. Meanwhile, this low-level turbulence is very violent and it will extend for a significant distance behind the mountain as well. Now, here's one thing that a lot of people don't think of. Often when they think of mountain wave turbulence, they instantly think of the Canadian Rockies. Really tall mountains, right? You know, tens of thousands of feet tall. Well, not tens of thousands, multiples, but you know, getting into the 12, 13,000 foot range, 14,000 feet sometimes. Although these effects are very common in the Rockies, you need to remember that they can also happen in the Appalachians, or that just like I showed you with that big, tall, very steep hill, hills as little as 300 feet tall do show some of these traits, just not on as big of a scale. So this diagram here shows some of the turbulence associated with mountains. Now, admittedly, we have a whole section on pilottraining.ca devoted completely to mountain waves and to mountain winds. So this is really just an introduction, this section. For the exam and practical flying, you're going to want to make sure you look at the mountain wave section. Okay, so here we have that flow, and then right in here you can see the upper waves at the upper levels. So these are moving up and down now. At the lower levels, oh gosh, that's where things get really challenging. You can see we have significant up and down. Notice as well we have cases where we can have clouds where the flow becomes reversed, known as rotor clouds. And these can be multiple, just spaced out along the wave behind the mountain itself. This low-level turbulence is really, really nasty. Now, when it comes to the upper levels here, really, it depends upon our speed as to whether we'll encounter turbulence or not at those higher altitudes. I mean, I've had many experiences with mountain waves, flying in, say, something like a 172 or a Cherokee. In this case, because they're pretty slow, as they fly, typically they just start to move up and down gently with each wave. You typically don't feel all that much. Yes, your airspeed indicator will fluctuate a little bit as you encounter each up wave and each down wave. You often don't have any other idea that it's happening because your altimeter might end up staying exactly the same. So, as a result, you just gently ride them out. Now, commercial airliners, however, going through these waves, well, just like that convection, because they're moving so fast, let's say they're moving this way, so fast, downdraft, so they feel it. Then suddenly updraft here, then suddenly downdraft here. So commercial airliners or very fast-moving aircraft, they will definitely encounter turbulence. Again, it's a function of the airplane and its motion through the air now. Down in these levels here, I don't care who you are going to experience turbulence. And oh boy, these rotor clouds, stay away. Just stay away. They rip things apart, literally. Like just many airplanes have been just totaled by them. Okay, let's look a little bit at mountain waves here. I told you that with mountains, it's nice when we actually get some clouds going. And that's because they can tell us about, well, where these waves are or that they're actually happening. So this cloud here is what we would call a lenticular cloud. You can see how it has a base area here, and then from there, notice how it's very, very smooth. What's happening is as this wave goes from down here and it moves upwards, remember the air is going to cool, it's going to expand, and if I have air in there that's near its dew point, that's going to condense, right? It'll become saturated. So these lenticulars actually show us the top of each wave crest. Okay, good. Mountain waves may be found as high as 40,000 feet. That's the official number to use for the exam, although research has shown that they sometimes extend up to 70,000 feet. Remember, 40,000 feet for the exam, though. Now, if you see a METAR, and that METAR reports either ACSL, altocumulus standing lenticular, or CCSL, cirrocumulus standing lenticular, then you know that mountain wave activity is definitely occurring. At the high levels, okay, yeah, we've got mountain waves going on. At the low levels, that could be trouble for sure. Here's a picture of some of those rotor clouds. You can see in the distance here, we've got the ridge of mountains right in through there. And then notice we've got the first rotor here, and then we've got the second rotor right here. If you could actually see these, they literally do appear to roll over. They almost look like somebody who's taking bread and kneading it. So you can YouTube this. You know, there's a couple of really good examples on YouTube where they actually show some rotor clouds. Just make sure that you look at a video where somebody actually knows what they're looking at and what they're doing. I've seen many YouTube videos that say, hey, that's a rotor cloud. And I look at it and I'm like, that is not a rotor cloud. So usually, you know, weather sites and stuff are the best. These possess the greatest amounts of turbulence, and whatever you do, avoid flying through them, between them, or below them, because I can promise you that there are going to be major areas of turbulence in here. And yes, must know this, very common exam item. Okay, now, what causes a mountain wave to form? Well, there's a few items that are key ingredients, but these ingredients don't guarantee that you're always going to get a mountain wave. That said, if we were going to get mountain waves, what would the key ingredients be? We got them right here. The wind velocity will be perpendicular to the ridge in terms of speed being 25 knots. Now, this is working like a crosswind component, so keep that in mind. If I have a wind blowing at an angle from the ridge, well, this speed of 25 knots is going to be what I'm looking for. What is the perpendicular component of the wind to the ridge? The wind speed will increase with vertical height in most mountain wave scenarios. And surprisingly, a lot of people look at this and they're like, when the atmospheric conditions are relatively stable. And people are like, oh, well, why is that? For this, I will quickly go over to the whiteboard and just show you why this is the case. Now, again, for this diagram, I'm going to assume that you've already watched the presentation on stability. We're going to utilize a profile view here, and then suddenly we have this mountain right in through here. So in unstable conditions, our airflow, if the wind is coming from left moving to our right, the airflow will move up the mountain, and then here, as it starts to accelerate up the mountain, if the conditions are unstable, what will happen is at some point, perhaps we might get a little bit of condensation going and some clouds starting to form. What will happen is this will just kind of start to feed off of itself, and then it will just kind of fire up and go straight up into the stratosphere. Meanwhile, yes, very potentially creating all sorts of thunderstorms as it moves. In a case, however, where the atmosphere is stable, well, you actually might not get a whole lot of cloud formation on the windward side. There could be some. There might not be as much. But now what will happen is that air, as it reaches the peak, it's going to be like, oh, you know what? Let's say that the temperatures here, we've got an inversion. So the temperatures are warmer aloft. This air is like, yeah, you know, I have no reason to head upwards, so I'm going to create a downdraft here. And then that's why we end up with the gravity wave now, because there's an inversion, stable level, so the air couldn't continue going up. So it says, okay, I'll go down, and now it starts to cycle up and down. So stable air actually facilitates the creation of mountain waves for me. All right, mountain wave turbulence, back on that slide. There we go again. Now, overall, mountain waves are a little bit like this picture. They tend to be fairly stable. And what that means is the position of each wave crest and each wave trough doesn't really change all that much relative to the surface. So, since mountain waves are fairly stationary, this can have differing effects for you depending on which way it is that you're flying. Let's imagine an airplane that is flying in this direction. Well, what's going to happen is that airplane's going to have a very high ground speed. So what will occur is this, high ground speed, so they're going to go through these mountain waves fairly quickly. They won't be in the mountain wave activity for a very long period of time. Now that said, think not only of your ground speed, but your speed through these individual waves. What's going to happen? You're going to go through those waves very quickly, right? So that's going to mean up and down, bam, 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 bam. So as you fly in this direction, you might encounter some turbulence if you're at a high speed in terms of flight speed. Meanwhile, somebody who's heading upstream towards the mountain ridges, well, now their ground speed is going to be really, really slow. So imagine them now, they're going to be kind of stuck in these waves. So the waves are going to have more time to move that airplane up and down. So guess what happens to the level of turbulence you experience? It's typically going to be reduced. Now, that said, again, airliners and fast airplanes will still have trouble going either way. Okay, so this describes what I just described right here. It's a good idea if you expect to encounter bumpiness to be sure that you slow your airplane down to the speed recommended for turbulent airspeed, or turbulence encounters being the, okay, VA, right, maneuvering speed. So that's a good speed to remember in our smaller aircraft. Okay, so this describes an airplane flying into the wind. Now that said, of course, you will be stuck in these vertical currents for longer periods of time, even though it will be a little bit smoother. So, you know, if you're heading towards a ridge, just as I showed you earlier, that could be a major issue. So here's the GFA with some nice examples of mountain wave turbulence for us. And you can see here in each and every case, like this is the southwestern corner of Alberta. Yeah, very good place for that to happen because a lot of those mountains in this area are very, very tall. That said, pretty much anywhere in BC up through the areas in northern Canada as well. And then in those areas, southeastern Canada too can experience these. So in this case, this particular GFA shows that we have a cold upper front approaching. Okay, so I'm starting to think maybe a little bit of frontal turbulence here. I mean, definitely look at this. We can see a low-level jet moving along in front of this cold front. This being an upper cold front, this is going to be near the level of the mountaintops. I'm pretty much thinking there's going to be mountain waves today. And look at that, right there, lee wave, mechanical turbulence. Notice the designator right here. Good golly, severe. And that goes from the surface up to 14,000 feet. Stay away, stay away. Over here, same idea. You know, that red area, lee wave, 7,000 feet to 14,000 feet. And then over here, once again, we can see another example. Moderate turbulence there, moderate turbulence there. Today here, really bad day. All right, so we're through the mountains now. Let's start to get into wind shear. Now, as I told you earlier at the beginning of this presentation, wind shear can potentially produce turbulence. Will it always produce turbulence? No, but the likelihood goes way up. Wind shear is a sudden change in wind speed and or direction in a short distance, and this results in a tearing or shearing effect. It creates those eddies for us. Now, when it comes to wind shear, remember, it can happen either horizontally or it can also happen vertically. The greater the change in the speed, speed again, and or direction, the greater the severity of the shear. Okay, so change of direction, more shear. This is no means exhaustive. The causes of shear, we'll actually go into some other causes as well. You'll see that there's more than just this. This type of wind shear here is kind of broadly categorizing them because we have jet streams that can cause shear. Then we have, say, lower level types of shear, which would include things like topography, fronts we could put in there, microbursts. So we'll take a look mostly in this presentation at the lower level types of wind shear. Okay, two broad, say, names for wind shear to start. If we have two winds flowing at different speeds in the vicinity of one another, we would call that speed shear. Wind blowing at different speeds at different altitudes create different turbulent eddies. So you can see in the diagram here, aloft, I've got a very fast moving wind. Right here, I've got a slower moving wind. So it's just like taking my two hands here. If my one hand is the speed of the wind aloft, what will happen is things in the middle will start to rotate, as we can see right in there. Now, another way that we could do this is through what we call directional shear. Wind blowing in different directions can also create these eddies and turbulence. So, in this case, we've got a wind aloft that's flowing westerly, and then down just a little bit lower, we've got that wind that is flowing easterly. So once again, we've got now two winds flowing in different directions. So one going this way, one going backwards. Again, we end up with rotation in the middle. And I've told you this several times already, so don't forget this here. Now, when it comes to wind shear, we have many items that can create wind shear at low levels. Wind shear for an airplane at a low altitude spells trouble. Low-level wind shear is technically defined as a significant non-convective wind shear that could adversely affect aircraft operation within 1,500 feet above ground level at an aerodrome. In a TAF or a METAR, wind shear will be reported with the top given first, followed by the forecasted wind speed and direction at that height. Okay. Now for you and your airplane, I'm going to come back to the METARs and TAFs in just a few moments. But for you in your airplane, you need to be aware that when you encounter wind shear, it's most problematical when you are close to the surface of the Earth. That's why METARs and TAFs report them 1,500 feet or below. The reason for this is, imagine that you are landing or taking off. It can have huge effects on what happens to your airplane. One example that I can think of is this. Let's imagine that you're in your approach and you are coming in for your landing. So you start your flare. And as you start your flare, suddenly you have a huge, powerful blast of wind, and you're suddenly going to start to float. Okay, so that's a wind gust. It's kind of like what wind shear does on us. When we have wind shear, now we have much bigger than just gusts. So if that's the case, what could it do to us? Well, one of two things. We will experience changes similar to like what we felt in that flare. If we encounter strong headwinds or a decreasing tailwind, we will call this increased performance shear. However, let's say that I have a headwind that suddenly gives up on me. It's not there anymore. So the speed goes from high to low. Well, my airplane's going to start to sink significantly. This would be what we call decreased performance shear. Decreased performance shear results from, or is a cause of, a reduction in my headwind, or could be a tailwind that rapidly increases. Okay, so some of you might be thinking, tailwind rapidly increasing. Well, in cruise, that's going to be good, Aaron. And you're right. In cruise, a tailwind is good. But when it's close to the ground and we're on our approach and we're coming in for landing and we suddenly have a headwind that disappears or a tailwind that disappears, that's going to be bad news. Okay, what I want to do to show you a few scenarios where increased performance shear could happen or decreased performance shear could happen, I want to go over to the whiteboard again and start to draw you out a few scenarios where this could happen and how it's practically going to affect you. All right, so we will erase our stable little mountain wave here. So let's draw a profile view of an airport and the airport environment. We've got the terrain there, and then let's imagine that we've got the runway right over here. Meanwhile, what we will also say is that aloft, we've got a very, very strong wind aloft. So this wind aloft is going to be on the order of maybe, let's say, 30 knots. Meanwhile, down here nearer to the surface, if we measured the winds, we discovered that, hey, they're only 10 knots. So I know if I'm an airplane that has been doing a cross country and I am on my way towards this airport, I know that somewhere between where I am here and my landing that I've got a wind shear zone. I don't know exactly where it is, but I know that it must exist. So let's say that maybe this shear zone is somewhere in through here. And I'm going to make it a very small layer because typically they're not all that thick. So we have our airplane and it begins its descent down through the shear zone. So here we are. We go through the shear zone, and we are approaching for what we hope would be something that would look like this. Okay, so that's the world's steepest approach angle. That said, as we suddenly go through this zone here, what will happen? Well, I've gone from a headwind of 30 knots to suddenly a headwind of only 10 knots. So that is a net change of 20 knots. So my airplane thinks that, well, it hasn't actually happened, but my airplane thinks, whoa, my airspeed just decreased. So guess what it's going to do? It's actually going to start to sink fairly rapidly. Now, eventually, that airspeed catches back up, and now what happens is we end up on the exact same path that we were before. So there's the sink, and now we would end up following that same path. So the initial happening is this. We end up undershooting in the case of decreased performance wind shear. So most pilots, what they will do is as they see this big sink, they will increase the power. When they increase the power, now their path looks like this. But then they continue on, ending up overshooting now. So the trick is this. When you feel this first sink, yes, you're undershooting, so absolutely you're going to need to add power. However, once you get to the proper glide path again, so once on glide path, what we will now need to do is reduce to original power. Okay. Let's erase all of this because we are next going to think about a situation where the opposite happens. So we'll just erase that. And now in this case, this 30-knot wind, well, guess what? It's reversed. I know the arrow on top is bigger, but please ignore that. Okay, for those of you who are purists out there, I'll make this arrow smaller. Ta-da! Now it's only 10 knots. Meanwhile, down at the surface, we've got the 30-knot wind. So now, what's going to happen? Well, originally, here's my originally planned approach path to the threshold. Now, as I encounter this sudden shear, this is reversed, plus 20 knots. So the airplane thinks, hey, I've got lots of additional airspeed. So guess what it's going to do? It's actually going to end up overshooting. So in this case now, we've got an overshoot. So if I did nothing, I would end up on this path towards the airport. No good, no good. So most pilots, what they will do is they see this overshooting, is they will do the right thing, and they will reduce their power. Okay, so I've reduced my power. Now what's going to happen is I'm going to sink back towards that glide path again. But if I keep my power the same, I'm just going to keep on going. That's vertical. That's really bad if you're going vertical. Anyways, ignore that, please. So once we reach our glide path, guess what we're going to do again? So once on glide path, we will now add to the original power. And then I will be back on my proper glide path. Okay. So encountering increased or decreased performance wind shear will cause my airplane to either start to undershoot or overshoot. I need to remember, am I going to add power or reduce the power? Then, once I'm on my glide path, am I going to do what with my power again? It's simply the reverse of what I did for the situation I was in. So keep these in mind as you write your exam, because there's many variations on how this could happen. Now, for everyday practical flying, as I mentioned too, keep in mind as well what is likely to happen with these winds that I've got here today. Am I in a situation as I approach my airport where I might have one of these potentially occurring? Okay, so here's some examples here of wind shear. In this case, right here, you can see that this particular pilot, actually it's not a PIREP, it's a METAR, but this particular case, they're reporting that there was wind shear encountered on runway 31. So I can see right here, really strong winds, incredibly strong winds, and at the higher altitudes, the wind was very different. Now, wind shear can cause erratic changes in the altitude or the attitude of the aircraft. Yes, if it's very bumpy, the wind shear. Also, as you've just seen, it can cause significant decreases or increases in our glide rate. Really critical, though, is the fact that as I encounter this wind shear, my airspeed will temporarily change. I showed you that on the whiteboard, how we had that net loss or net addition. The loss is the really bad one. If I end up losing that headwind, I'm going to lose my airspeed. I'm going to potentially be closer to the stalling speed of my aircraft. So, as you come in, you're on your approach, you've identified that there might be a situation where you have the potential for wind shear. It might be a good idea to have your approach speed bumped up just a little bit. Now, fortunately, for smaller airplanes, wind shear is actually less of an issue than bigger airplanes. And that's because smaller airplanes don't have as much inertia. So it encounters the wind shear, it very quickly settles to what the new wind is telling it to do. Bigger airplanes, however, they just keep plowing through. They take a long time to change their inertia. So an airliner encountering wind shear is going to have actually a lot more trouble than a smaller aircraft would. That said, still want you to have a good respect for wind shear. Okay, the following guidelines are used to establish, report, and forecast significant non-convective wind shear. A wind speed that changes more than 25 knots within 500 feet AGL, a wind speed that changes within 1,000 feet AGL, 40 knots or greater, and then a wind change by more than 50 knots within 1,500 feet AGL. Any pilot that reports a loss or a gain of indicated airspeed of 20 knots or more within the final 1,500 feet AGL also qualifies as wind shear. And that's possibly why that ended up being the case on the METAR that we saw together there. So what are some causes of low-level wind shear? You can see there's many. Low-level nocturnal inversion, a low-level jet, microbursts, virga, which are related to thunderstorms, and incidentally are actually a type of microburst. Sometimes we'll hear the term dry microbursts, and we'll look at those in a moment. Rotor clouds, which we've already discussed, those nasties with mountain waves, and then funnel clouds and thunderstorms. So let's take a look at each one of these individually now. The first one is the low-level jet. Now, these are often associated with a frontal system. A powerful jet of cold air, typically with a cold front, or even warm air with a warm front, can often be following up just behind the frontal zone. So in this case right here, we've got a very powerful low. We had a cold front that was stretching out somewhere in this area here, and you can see that cold air coming down at high speed around that low. Meanwhile, on the side here where the warm air is, again, we probably had the warm front somewhere right in here, just kind of before the trowel. And in this case, a low-level jet, you can see 55 knots, very fast-moving jet. Look at this one here from the cold air. Yay! Low-level jet, 75 knots. So for those of you who studied fronts, and we said, well, cold, dense air moves faster than warm air, here's a very vivid example of that, 75 versus 55. Over here, once again, we've got a cold front right there, and you can see that jet of air right in here following that cold front. In this case, this one's a quote-unquote slow one, only 50 knots. That's still pretty fast. These are found typically at heights of 700 to 2,000 feet AGL. Now, these are closely related to low-level jets, but low-level jets are typically much greater in terms of their extent geographically. Both of them, however, can behave very much the same. So some of you might be looking through this, you might be like, well, this seems a little bit confusing. That's because they are fairly close to the same. It's just a matter of how far geographically do they extend. Low-level jets that are nocturnal inversions tend to be on slightly smaller geographical scales. And here's how these get to forming. During the daytime, remember, what happens is we've got solar heating. We've got vertical currents that are moving up and down. So if I've got winds aloft, this sun will, through convection, start to mix these winds and start to pull them down to the surface. So what that does is that has a net effect of slowing these winds aloft down. Now, imagine nighttime happens. And particularly so, if we have an inversion, we can end up with, well, now we don't have those currents flowing. So as a result, that's going to cause these winds to be just a little bit faster. But also what starts to happen is the Earth radiates some heat off and up into the higher levels. So that warmth will actually help speed things up as well. So I'll end up with a very fast jet of air, typically, again, 700 to 2,000 feet AGL. Now the speeds can vary from as little as only 8 knots at the surface, very gentle, to 25 to 40 knots at the jet maximum. Above this maximum, typically what will happen is the wind speeds will decrease again. So we usually have the maximum speeds kind of right in here near where the inversion is. And then they start to slow down a little bit. Now notice this, in extreme cases, some of these winds have been observed as fast as 65 knots. So imagine you're flying at night and one of these forms. Imagine that it forms at a very low altitude. So you're coming in at night, everything looks good on your approach, and all of a sudden it seems like the world drops out from below you because your airplane goes down at a rapid not at a rapid speed, but it goes down at a rapid rate. It can be very surprising. And again, at night, you might want to be aware of if the conditions are going to be conducive for such an inversion. If I've got an inversion developing and I've got a clear, brightly starlit night, the odds of this occurring when I'm going night flying go up. Now, another type of low-level wind shear is something known as a microburst. And we will talk about this a little bit more as well in the thunderstorm sections. So this is an introduction. Thunderstorms can produce a tremendous amount of wind shear. It's partly why they were called TNTs, turbulence near thunderstorms. One of the worst types is the microburst, but more on that in just a moment. When we have a thunderstorm, what often precedes it is something known as a gust front. And that gust front on its own can suddenly cause the winds to change by 180 degrees or more. Behind the gust front, we will frequently have sudden huge swaths of rain falling. These are downbursts. Downbursts can produce some pretty violent turbulence as well. The rain falls down and it suddenly spreads outward. Extremely intense downbursts, those can be known as the microburst. Extremely powerful downbursts with extremely violent winds that last for a few minutes and are typically only about a mile wide. Now, I'm going to go over to the whiteboard because this principle here actually leads us into the next slide, which is something known as virga. So let's go to the whiteboard and we'll draw out a typical microburst for you. All right, so here goes our performance shear. We're going to kind of try to view, this one will be a little bit more of a challenge to draw, but let's see if we can pull it off here. So I'm going to draw, first of all, let's imagine a cloud base here. So there we go. There's the cloud base there. And then I think what I'll do is at a lower altitude, we'll put in the ground. Okay, so the ground like this, something like that, something like that. Okay, so this is the ground. And then we've got, at a much higher altitude, the actual cloud base of the thunderstorm itself. So what happens with microbursts is we can have an area of rain that starts to fall, very, very cold air, and of course it's going to go through the clouds and then proceed downwards. So this cloud becomes very, very angry. It starts to lower its base just a little bit. And then that rain just starts a falling in earnest. Now, once this rain gets to the ground, it's dragging with it extremely cold, dense air as well. Super cold, sometimes in the order of like very close to, I mean, this is way up high in the upper atmosphere, so this can be like just temperatures of like minus 10 degrees Celsius or even lower. It does warm up a bit as it gets closer to the surface of the earth, and that's why it kind of stays as rain. But once it strikes the earth, all this cold, dense air and all this rain, it has nowhere to go. So it's going to suddenly whirl outwards like this and then come back up and swirl in like that. So like that, like that. So what you have in kind of a donut shape all the way around this downburst is you end up with these swirling, powerful eddies, just like that. And typically, as mentioned, they're about a mile wide. Okay, so let's look at this from a profile view. What would this look like? I've got enough room over here. So here's the profile view. Here's our angry cloud up here. And then, of course, we now have that cold, dense air falling down. Strikes the earth and out like that. Same over here on this side. So you can kind of see a problem here now, because imagine that I have a runway maybe over here. And let's say, not a good idea, but there have been several airliners that have come to severe grief because of this. You are approaching like this. That's what you were hoping your approach angle would be. Well, guess what? Here I encounter this severe updraft. The airplane starts to go way up too high. So guess what I do? I reduce my power. So as I reduce my power, now the airplane starts to go down like I want it. But then it gets caught in the downdraft. So now it really goes down, and it crashes right there. There have been many accidents in the commercial aviation world where that exact scenario has played out. And one well-known example that happened in Dallas really got the research going for what these downbursts and microbursts were and how we could better avoid them. I think before I go over to the whiteboard, though, what I'm going to do is I'm actually going to change this microburst into a case with what we just talked about, or where I've briefly mentioned something known as virga. Now let's imagine this scenario. So I will erase the microburst right here. I almost don't need to erase this microburst because really it will still happen even with virga. Virga and dry microbursts tend to occur in cases where the air is very, very dry at a certain level. So let's imagine here we had very dry air. What will happen is this rain falling will suddenly evaporate. So we will actually see a waterfall falling out of the cloud to an altitude, who knows, this could be a few thousand feet. But suddenly, all of this air sucks the moisture and rain out. And it seems like the rain suddenly disappears right here. Well, as a pilot, I might think, hey, that rain only goes partway down to the ground, so I think that it's going to be safe to fly and to fly below that little rain shower there. Bad move. Remember, in order to evaporate, I need to take heat from the atmosphere. So if I take heat from the atmosphere, remember this was cold, dense air to start with. Now it becomes even more cold and more dense, and guess what happens to its speed towards the ground? Whoa, it increases significantly. So now guess what happens at the ground? I don't see any rain. I don't see anything to indicate that there's a big, powerful downburst, but there sure is. And then we have that huge microburst right on the ground here. No rain to show that there should be that happening. That is a dry microburst. Okay, so let's head back over to the presentation then here. And the next slide should be virga. And it is similar to a microburst. Awesome. Virga hazard is, remember I showed you that cold, dense air getting accelerated? So in the virga, yeah, you're going to encounter a downdraft, but even below where the rain seems to end, you could still have a very powerful downdraft. Okay, funnel clouds, stay well clear. I don't think I need to say too much about this, except for this was one that happened not too far from home. And then turbulence at the high levels. We do have a section on jet streams. We briefly talked about them as well in the winds section. So I'm not going to spend too much time here talking about clear air turbulence. It's frequently associated with jet streams. Notice that jet stream turbulence is the greatest to the left of the jet core when facing downstream. So in this case here, this jet is actually moving from you, the camera, in this direction, so that's downstream. So right like that. So you can see very clearly the areas of turbulence off to the left and off to the left. A sharp temperature gradient, mountain waves, or wind profiles that vary significantly can also cause clear air turbulence. Those mountain waves, if I'm an airliner flying through them very fast, that would be classified as a type of clear air turbulence. All right. When it comes to reporting turbulence, well, we have some very specific reporting criteria. Now, that said, I do want you to think about turbulence reports when you read them, though. Whenever you see a PIREP with turbulence, consider carefully what type of an aircraft it is. For example, let's say that I'm about to go on my cross country, and I read a PIREP, and it says that, oh, look at this, you know, an A320 reported moderate turbulence in this area. All right. If an A320 reports moderate turbulence, you're flying in your little 172, 152, Katana, whatever it may be, Cherokee. What do you think the turbulence is going to be like for you in that little airplane? If you said it's going to be big, Aaron, you're right. So when it comes to reporting turbulence, if a pilot is reporting it, they're reporting it based on these criteria here, what they actually felt. That said, what a pilot feels will partly be based on how big or how little their airplane is. Okay, let's look at the criteria and know this for the exam. Remember this for the exam. Light turbulence is classified as slight erratic changes in altitude and or attitude. Less than 15 knots in terms of the airspeed fluctuation. Moderate turbulence, greater intensity than light chop, usually causes bumps or jolts, but aircraft does remain in control at all times. Severe, large abrupt changes, momentarily out of control, airspeed fluctuations in excess of 20 knots, or 25 knots, correction. This is pretty nasty, and I have experienced that. It's not fun. Extreme. Airplane is violently tossed, control is impossible, and it may cause structural damage. That one never experienced, nor, to be honest, do I ever want to. Light chop, slight and rapid rhythmic bumps without changes in altitude or attitude. And then over here on the GFA, you can see that there is a legend for you. You can see that if we've got one bump here, that's classified as moderate turbulence. If we have severe turbulence, then it gets capped. Kind of like, it's really bad. And the last little bit of turbulence, I think I'm going to leave that for you to study on your own. Maybe if you have read through the theory of flight section already, or even briefly we touched on it in the P-star section, you can do this on your own, maybe a little bit of refreshing. Wingtip vortices, well, there's an example from just a crop duster. Whee! Aircraft are capable of leaving significant turbulence in their wakes, and greater detail in wake turbulence and the theory of flight sections. So there we go. That's it for turbulence. Not very bumpy here in the studio, except for, you know, in the vicinity of that little flame and the match and blowing out the candle. Till next time, smooth flying for you, I hope. I'm Aaron for pilottraining.ca.